Okay, have you noted down? Right? So look at here. So this is the integrated circuit as we, okay. So as we already know, generally, I think that you have already uh, seen the integrator in PDC, right? So usually we build the integrator circuit with the help of the passive components like resistance and capacitors. So that is known as passive integrator circuit, and also we know that the integrator circuit acts like a low pass filter, isn't it or not? Right? So this is also an integrator, as here we were using the active component like op amp. Wherever we use the active components like op amp, the transistors or diodes, generally those circuits are called the active circuits. So here we have constructed or designed the integrator using an op amp. So obviously this is called an active op amp integrator. And of course, this is a ideal version of integrator, right? So there is also a practical version of integrator. So before going to that, let us see the ideal version of integrator and what are its inputs and what are its outputs and what are the drawbacks of this circuit. So before going to that, let us start the integrator. So basically what is meant by integrator? Why we were calling this as an integrator? This is very much obvious that your output will be integration of your input, whatever input that you have been given. It produces this circuit will produces the integrated output for whatever input that you have applied. That's why we were calling it as integrated circuit. So if you can see here, this is the active ideal integrator op amp integrated circuit. So let us start the analysis first. So let us start with, so here this is clear that at node B, uh, actually this terminal have been grounded, and of course the voltage at this node, that is, let it be VB, okay? So at this node is 0, right? So according to the virtual ground concept, if the voltage at this node is 0, obviously we can consider that voltage at this node, that is node A, is also equals to 0. So that's why VA equals to VB equals to 0 is considered. As this is 0 at this node, it is 0. We have considered the virtual grounding concept. So according to that, we have taken also considered that voltage at this node A is also 0. That's why therefore we have got VA equals to VB equals to 0, right? So that was the first step that we have done. And coming to the next step, so we already know that input current of op amp is 0. So whatever the current that was flowing through the entire circuit is considered to be equal. Okay, so let the I be the entire amount of current that was passing through the circuit. Now from the input side, let us write the current equation. So from the input side, what could be the current equation? I equals to, yes, V in minus VA by R1. Isn't it? From the input side, my current equation is I equals to V in minus VA by R1. And already we have considered that VA is equals to 0. So this equation can be rewritten as V in by R1. So I equals to V in by R1. Now from the output side, that is considering this current, right? So how can I write the current equation is I equals to, as we have the capacitor over here, generally it is represented as differentiated voltage, isn't it? So that's why I have written it as I equals to CF D of VA minus V naught by dt, right? So this is the current equation from the output side. Is that clear? Yes, is that clear? So from the output side, as we have the capacitor and we represent, if we have the capacitor, generally we represent it in the form of current equation. Excuse me. ఎట్లా రాస్తామండి కరెంట్ ఈక్వేషన్ కెపాసిటర్ ఉంటే డిఫరెన్షియేటెడ్ వోల్టేజ్ కింద రాస్తాం కదా సో దట్ ఈస్ వాట్ ఐ హ్యావ్ రిటర్న్ హియర్ సో I equals to CF into dVA minus V naught by dt. So as we know that again this VA is 0. So if it is 0 again my equation becomes I equals to minus CF dV naught by dt. Right? So this is the first equation, that is V in by I equals to V in by R1 is the first equation, and I equals to minus CF dV naught by dt is the second equation. Now already we have considered that the amount of currents that was flowing through the entire circuit is equal. So I can just equate 1 and 2. So if I equate 1 and 2, I'll be getting V in by R1 equals to minus CF dV naught by dt. Okay, so I have equated first, this is considered to be the first equation and this is considered to be the second equation. So I have just equated 1 and 2. So obviously, finally I have got this expression. Now I'm going to simplify this expression. So I have been about to integrate on both sides. Okay, so if I take integration on both sides, obviously what will happen is, of course, this will be represented, if I integrate, this will be represented as integration of 0 to t V in by R1 dt equals to minus CF integration of dV naught by dt. So this term will simply become V naught. Okay. So this term will simply become V naught, and keeping V naught here by just moving this CF to this side, my final equation will be V naught equals to minus 1 by R1 CF integration of 0 to t V in dt. Okay. So this is 1 by R1 CF is considered to be the constant value. Now this is very much clear. If this is considered to be the constant value, this is very much clear that your output voltage of this circuit is integration of your input voltage. Okay, so this is justified that this circuit have been acting as integrated circuit, right? So this is the derivation for ideal active integrator. Just go through this. Just take it down. So if this is over, let us go to the next channel. Yes, I hope this is over for you. Okay, right. So the previous equation, that whatever you have derived, it was clearly saying that the output is minus 1 by R1CF times integral of your input voltage. So R1CF is called the time constant. Okay, so you can see some other circuit, right? Additionally, where a compensation resistance have been added, right? That is previously in the previous circuit, you don't have any resistance to this non-inverting terminal, right? Additionally, here you can see this is a small modification of the previous circuit. You can see a small resistance which was added to the non-inverting terminal, and this resistance will be acting as compensation resistance. So this modified circuit generally is used for bias compensation. So no doubt the circuit will be acting as an integrator, but a small modification is that additionally we have added a compensation resistance at non-inverting terminal. Of course, this doesn't makes much change. Simply this is used for bias compensation if necessary. Now let us see what are the various outputs that we'll be going to get when you apply different kinds of inputs. So this is very important. Note down each and every figure. Okay. Now let us start with, here you can see an example. So let us start with step input signal, right? So in the figure you can see that we have applied input voltage is applied in the form of step input, right? Now let us see what is the output that we are going to obtain. So just do a small mathematical analysis, right? So as I have told you that this is a step input. So let V in of t, that is input voltage, is equals to sum A. Okay. Now, if just substitute this directly in this equation, of course, anyways, R1CF is considered to be some constant, right? So let that be 1 for a while. Assume that time constant RFC1 to be 1 for a while. Previously మనకి ఇక్కడ వచ్చింది కదండి, దీన్ని కాసేపు ఎజ్యూమ్ చేసుకుందాం, 1 అని ఎజ్యూమ్ చేసుకుందాం, ఎందుకంటే ఇది ఎట్లాగో కాన్స్టెంటే కాబట్టి నథింగ్ మచ్ టు డూ అబౌట్ ఇట్. సో ఫర్ ఎ టైమ్ బీయింగ్, for simple analysis, let us consider that RFC1 is 1. So if RFC1 is considered to be 1, the time constant is considered to be 1, then obviously just substitute, simply substitute. And one more thing I have forgot to say is, here I have got the negative sign. So this negative sign is representing you that this is in the inverting configuration. If you observe, the input is applied to the inverting terminal and your non-inverting terminal is grounded. So this is in the inverting configuration. That's why here we have got the negative sign, right? The going to this thing. So as I have considered 1 by, R1CF is 1. So obviously that will become 1. So simply substitute in this equation, that is V naught of t equals to minus integral of 0 to t V in t dt. So if you substitute there this A, right? So as this is a step input, obviously this is considered, this A is considered to be what? Something like constant, isn't it, or not? So if this is considered to be constant, this was taken out of the integral part. Now just your time limit has been integrated. So if that was integrated, look at here what I have got after the simplification. That will be equal to minus A of t, where the integral limits is from 0 to t, right? So initially your lower limit is 0, so that's why your output is 0, and your upper limit is t, so simply that output is minus 80. That means finally your output voltage will be at will be equals to minus 80. అంటే ఇక్కడ చూడండి నాకు అవుట్పుట్ ఎలా వచ్చిందో చూడండి, 0 to 2 టైం లిమిట్ అనుకుంటున్నాను కాబట్టి ఇక్కడ నాకు ఎట్లా వచ్చింది అవుట్పుట్, స్టెప్ ఇన్పుట్కి ఫస్ట్ 0 అయింది, 0 అయ్యి అక్కడి నుంచి నాకు స్లోగా డిక్రీజ్ అవుతా ఫైనలీ ఐ హ్యావ్ గాట్ సంథింగ్ like minus 80. అంటే స్టెప్ ఇన్పుట్ ఇస్తే నాకు వచ్చే అవుట్పుట్ ఏంటండి? What is the output that I am going to get if I apply the step input? What is this? Yes, ramp output, isn't it or not? ఎవరు మాట్లాడేంటండి? క్లాస్ మొదలైన దగ్గర నుంచి నేనే మాట్లాడుతున్నాను, అసలు వింటున్నారో లేదో కూడా అర్థం కావట్లా. Is it clear or not? సార్ మీరు మాట్లాడేంత వరకు క్లాస్ చెప్పండి, నేను ముందుకెళ్ళను. So as I have applied the step input after the mathematical calculation, I have got the ramp output. Is that clear or not?
Yes, ma'am.
Right. Similarly, so this is one of the input and the output that we have been getting. And similarly, look at here. So previously I have applied the step input and I have got ramp output, right? So if I apply square wave as input, if I apply square wave as input, what could be the possible output that I am going to get? Yes. So if I take the square square input, generally the current integral limits will be taken in between, of course, 0 to t, but they will be varying from, for one time interval they will be varying from 0 to t by t, and for one time interval they will be varying from t by 2 to capital T. Yes or no? If you can look at here in the figure, right, as this is a square waveform, so one part of the interval is varying from 0 to t by t, and other interval is varying from t by 2 to t. Yes. So as usual, my input is considered to be A here, right? Input voltage is considered to be A here. So if I consider my input is A, so from 0 to t by 2 it will be A, and from t by 2 to t it will be minus A. So if I substitute that for the output voltage, obviously what I am going to get is from 0 to t by 2, my output voltage after the integration, my output voltage will be minus 80, and from t by 2 to t, my output voltage is plus 80. So if you can see here, as usual, నాకు ఇక్కడ ఈ పాజిటివ్ స్టెప్ ఇన్పుట్ కి నాకు నెగటివ్ గోయింగ్ స్లోప్ ర్యాంప్ వచ్చిందండి, that is 0 to t by 2, where I have got minus 80. Similarly, for the negative cycle, see, look at here, my minus 80 have been increasing to 80, right? సో ఇందాక స్టెప్ ఇన్పుట్కి ఏదైతే వస్తుందో స్క్వేర్కి అదే వస్తుంది, ఎందుకంటే స్క్వేర్ ఇన్ కంటిన్యూస్ ఫార్మేషన్ ఆఫ్ స్టెప్ ఇన్పుట్ కదండి. సో ఆబ్వియస్గా నాకు ర్యాంప్ కంటిన్యూస్ ఫామ్లో వస్తుంది. అంటే నా స్క్వేర్ వేవ్ ఇన్పుట్ సిగ్నల్కి సింపుల్గా నేను ఏం చెప్పొచ్చు అంటే ఐఎమ్ గెటింగ్ ట్రయాంగులర్ వేవ్ ఫామ్ అని చెప్పి చెప్పొచ్చు అనమాట. ఓకే, ఇస్ దట్ క్లియర్ నౌ? ఇస్ దట్ క్లియర్?
Yes, ma'am.
So for step input I have got ramp, for square wave I have got triangular wave. Now look at so let us say for sine wave, or what is the possible output that I am going to get? Obviously, so for sine wave means my input voltage is obviously, let it be some Vin equals to Vm sine omega t. If I integrate Vm sine omega t, generally I'll be going to get cos. So for the sine input, the output waveform that I'm going to obtain is cos wave. For sine wave input, I'll be getting cosine output. So here are the list of waveforms. So first step, I have got ramp. For square wave, I have got triangular wave. For sine wave, I have got cosine waveform, right? So just take down this concept. if input and output waveforms. So after that, we'll go for the frequency response of ideal integrator. So this is the step input. Right. So if this is on, just take down this also. ఇది ఇంపార్టెంట్ అండి, అందుకని ఇంతసేపు ఇస్తున్నాను, నోట్ చేసుకోండి. Just take down this also. After that, let us see the frequency response. If that was over. Let us see the frequency response of integrator. So as we already know that my output equation is V naught of t equals to 1 by minus 1 by R and CF, integration of from 0 to t V in dt, isn't it? So here what I'm going to do is just take the Laplace transform. That means if I apply the Laplace transform for this equation, I'll be going to get V naught of S equals to minus 1 by S R1 CF V of S. This is not T, this is S. So for this equation, whatever the output equation that I have got for the ideal integrator, that I have considered, and for that equation I have applied the Laplace transform. So after the application of the Laplace transform, I will be getting V naught of S equals to minus 1 by S R1 CF V in V in of S. So in the place of S, just replace S by j omega. So if I replace S by j omega, I'll be going to get V naught of j omega equals to minus 1 by j omega R1 CF V in of j omega. So what you'll do is just take this V into this side and you will be going to get V naught by j omega. V naught j omega by V in j omega equals to minus 1 by j omega R1 CF. So V naught by V in means this is nothing but gain. So this is considered to be, if it is considered to be the magnitude of gain, then I'll be going to get A equals to magnitude of minus 1 by j omega R1 C1. So general magnitude అయితే negative sign తీసేస్తాను. Okay. And of course, 1 by j is considered to be 1, isn't it or not? Right? It is considered to be 1. So obviously I am going to get A equals to 1 by omega R1 CF, where in place of omega I'll be just using 2 pi f. So finally I'll be going to get A equals to 1 by 2 pi f R1 C1. So this is the magnitude of gain. Okay. So let us write. So what I'm next step, what I'm going to do is just simply I was applying 20 log. Simply I was just calculating the gain in dB. So here I'll be taking 20 log if I consider, uh, to calculate the gain in terms of dB, right? I'll be writing the expression like 20 log A equals to 20 log 1 by 2 pi FB. That means here simply I have considered that F equals to FB, where my output gain becomes 0. అంటే మనం ఆపాంప్కి ఎట్లా అయితే ఫ్రీక్వెన్సీ రెస్పాన్స్ క్యాలిక్యులేట్ చేసామనండి, డిఫరెంట్ వాల్యూస్ దగ్గర ఇక్కడ కూడా మనం ఫ్రీక్వెన్సీ రెస్పాన్స్ క్యాలిక్యులేట్ చేస్తాం అన్నమాట. ఓకే. సో నాకు ఎఫ్ ఈక్వల్స్ టు ఎఫ్బి అయినప్పుడు జనరల్గా ఇది 0 అయిపోతుంది బేస్డ్ అపాన్ యువర్ వాల్యూ ఉంది. సో 0 dB వస్తుంది. 0 dB వచ్చిందంటే మామూలు dB కాకుండా అయితే యూనిటీ గెయిన్ వస్తుంది. ఓకే. After if you see the figure, it will be very much clear. అంటే నువ్వు ఫ్రీక్వెన్సీ అప్లై చేయడమే నాకు ఇంటిగ్రేటర్ ఏమవుతుందంటే సడన్గా ఫాల్ ఉంటుందండి. సడన్గా ఫాల్ అయ్యి 0 dB అయిపోయి అంటే యూనిటీ గెయిన్ వచ్చేస్తుంది అనమాట. సో ఇది కన్సిడర్ చేసుకుంటే నాకు ఎఫ్బి ఏమవుతుందనంటే ఇది కన్సిడర్ చేసుకుంటే A equals to 1 by 2 pi FB R1 C1 which is equals to 1 కదా. ఈ ఈక్వేషన్ నుంచి నాకు FB ఏమవుతుందంటే FB equals to 1 by 2 pi R1 CF. సో గెయిన్ ఎప్పుడైతే నాకు 0 dBకి డ్రాప్ అయిందో అక్కడ నాకు యూనిటీ గెయిన్ వచ్చేస్తుంది. దాని నుంచి నాకు FB వాల్యూ ఏమొచ్చిందంటే 1 by 2 pi R1 CF వచ్చింది. సో ఇఫ్ యూ కెన్ సీ ద ఫ్రీక్వెన్సీ రెస్పాన్స్ హియర్, లుక్ ఎట్ హియర్. సో ఇనీషియల్గా నాకు గెయిన్ ఇక్కడ ఎక్కడో ఉందండి. సో నాకు ఇంటిగ్రేటర్ ఏంటంటే గెయిన్ విల్ డిక్రీజ్ విత్ ఇంక్రీజ్ ఇన్ ద ఫ్రీక్వెన్సీ. నేను ఎఫ్ ఈక్వల్స్ టు 0 దగ్గర తీసుకుంటే ఇదే ఈక్వేషన్ కావాలంటే చూడండి. ఒకవేళ నేను ఎఫ్బి ఈక్వల్స్ టు సమ్ 0 అనుకున్నాను అనుకోండి. 0 అనుకుంటే నాకు గెయిన్ ఏమవుతుంది, ఇన్ఫినిటీ అవుతుంది. 0 కాకుండా ఏ అదర్ వాల్యూ అయినా రెడ్యూస్ అయిపోతుందండి. ఓకే, అదే చూపిస్తున్నాడు ఇక్కడ. సో లెటర్స్ సే నాకు ఎఫ్ దగ్గర చూడండి గెయిన్ ఎంత హై ఉందో, రైట్? హై గెయిన్ ఉంది. నాకు ఎప్పుడైతే ఫ్రీక్వెన్సీ పెరగడం మొదలైందో స్లోగా రెడ్యూస్ అయిపోయి 0కి వచ్చేసింది, రైట్? సో ఐఎమ్ కన్సిడరింగ్ సమ్వేర్ అట్ దట్ ఫ్రీక్వెన్సీ టు బి వేర్ ద గెయిన్ రెడ్యూసెస్ టు 0 dB. ఆ ఫ్రీక్వెన్సీ నేను ఎఫ్బి అనుకున్నానండి. సో దిస్ ఈస్ హౌ ద ఫ్రీక్వెన్సీ రెస్పాన్స్ కర్వ్ we get for an ideal integrator. So the gain rolls off at a rate of 20 dB. సో నాకు ఫ్రీక్వెన్సీ పెరిగే కొద్దీ సడన్ ఫాల్ ఉంటుందండి నా గెయిన్లో. సడన్ ఫాల్ ఉండి 0 dB అయిపోతుంది అనమాట. ఇది ఫ్రీక్వెన్సీ రెస్పాన్స్ కర్వ్ ఫర్ ఐడియల్ ఇంటిగ్రేటర్. So hope this is clear for you. Now I think it is clear. Frequency response curve of ideal integrator. Yes. అందుకనే ఇది ఇంటిగ్రేటర్ లో పాస్ ఫిల్టర్ కింద యాక్ట్ చేస్తుంది. లో పాస్ ఫిల్టర్ అంటే ఏంటి? ఓన్లీ లో రేంజ్ ఆఫ్ ఫ్రీక్వెన్సీస్ అలౌ చేస్తుంది కదా. నాకు లో ఫ్రీక్వెన్సీస్ దగ్గరే గెయిన్ ఉంది, హైయర్ ఫ్రీక్వెన్సీస్కి వచ్చేటప్పటికి గెయిన్ 0 అయిపోయింది అంటే హైయర్ ఫ్రీక్వెన్సీస్ అలౌ చేయట్లేదు అని అర్థం అనమాట. రైట్. సో దట్స్ వై హై ఫ్రీక్వెన్సీస్ దగ్గర మాత్రమే నాకు గెయిన్ వస్తుంది కాబట్టి సో హై ఫ్రీక్వెన్సీస్ దగ్గర గెయిన్ వస్తుంది కాబట్టి సారీ అక్కడ మాత్రమే లో ఫ్రీక్వెన్సీస్ దగ్గర మాత్రమే నాకు హై గెయిన్ వస్తుంది కాబట్టి దిస్ ఈస్ ఆబ్వియస్లీ ఇంటిగ్రేటర్. we are saying that integrator is acting as low pass filter. Okay, so this is about the ideal integrator. So there are some errors regarding this ideal integrator. So let us see those errors in the next class, and that's why we were going to a small compensation circuit which we were calling it as a practical integrator. So that we'll see in the next class. Hope the class is clear for you.